Okay, let's get started again. All right, so this is the third hour of Physics 1C. We're just going to do a brief kind of just review of Physics 1C. Okay, so what have we talked about this semester? So we can kind of like break down the topics into just kind of like four basic subjects that we've discussed this semester, you could say. And what those are electrostatics, electrodynamics, and then magnetostatics. Can't spell this. Yeah, better way to just say this instead of magnetostatics actually is just magnetism, honestly. And then finally is electromagnetism, which is really what this course is all about. Okay, for electrostatics, what did we do? Well, we talked about things like electric charges, forces, fields, electric potentials, all of these different things, right? Capacitors, right? And the vast majority of all of this is basically just governed by Gauss's law. Gauss's law kind of describes how most of these systems behave. It allows you to derive things like Coulomb's law. It allows you to talk about what electric fields are, electric potential, which we call voltage, and capacitors, all this type of things, right? All of these are contained within this concept of electrostatics. Situations in which you have electric charges that are at rest, basically. All of these concepts show up there. The definition of what the electric field is, which is basically just that the force placed on a charged particle is equal to the size of the electric field multiplied by the charge. Coulomb's law is really kind of just contained within that idea, because if you can write down the electric field for a point charge, which we used over and over and over again in this class, the electric field of a point charge, kq over r squared, then you can get from the definition of the electric field back to Coulomb's law. Electric potential, which we defined like this: delta V was equal to the integral negative from a to b of E dot ds. And yeah, I mean, looking at that equation doesn't really help very much, so it's really better to just remember that electric potential is the amount of energy per unit charge. And then we learned about capacitors, where the charge on a capacitor is equal to the capacitance multiplied by delta V, the potential difference between the plates, or the potential difference that's applied to the plates. All of those topics show up in electrostatics. There's a lot of different things you have to do in here that are quite complicated, such as to find the electric field for different types of shapes of objects. That tends to be the thing about a 1C that really throws people off. But hopefully by now you've all kind of, at least, I don't know, mastered, but gotten pretty good at being able to describe the type of electric field that's produced for like an infinite line of charge, for a sphere of charge, for a cylinder of charge, all these different arrangements that you might have. I've talked to people that are engineers, and they always tell me when they look back to their 1C classes, they liked everything they did. They liked the circuit stuff. They really found induction to be cool, and they liked magnets and all that stuff. But the one thing that everybody hates is all these different electric field derivations for different shapes and stuff. And it's understandable. It's pretty complicated. Okay, from there we move into electrodynamics, which leads to the phenomenon of things like current. So electrodynamics means things that are changing or moving, right? So electric current, the concept of resistance, which is the idea that you can have a resistance to the flow of current for a given electric potential. And what else is there with dynamics? I guess there's the idea of electrical power, that power is equal to I times delta V. There's the relationship between current and resistance, which is delta V equal to I times R. What else did we discuss about moving electric charges? It's not much, right? We talked about DC circuits, which we could talk about like a series of resistors. We could talk about parallel resistors. We could talk about what are called RC circuits, where you put a resistor and a capacitor together, and it leads to this relationship about how the charge on the capacitor works as a function of time. And we found that it was equal to something like Q max times 1 minus e to the negative t over rc. That was an example of something we discussed, where this RC is like a time constant that tells you that when you have an RC circuit, you can use it to make basically timing elements inside of a circuit. Just going to check real quick to make sure that I'm not missing anything. I think that's pretty much it. That's a very short part of this course, because as soon as we stop talking about that, and as soon as we have the idea of electric currents, we just almost immediately go into talking about magnetism, I believe. Just looking at the topics in these courses, this stuff. Yep, resistivity, EMF. Oh, Kirchhoff's rules. That's a pretty big topic that shows up in here that's very useful. There's Kirchhoff's rules. We use that a lot in this class. Yeah, that's pretty much it. And then we go into magnetism. And with magnetism, we start to learn that electric currents actually produce magnetic fields. And when you have static currents that aren't changing, static current's probably a bad way to put it, but if you have an electric current that's constant, then you can do things like you can find that there's a magnetic field that's produced around a current-carrying wire that looks something like this. You have a long straight wire. We learn about the idea of like the Biot-Savart law, which is kind of our fundamental experimental relationship that allows us to define how magnetic fields are produced, and eventually we get a better version of this. I'm just kind of making sure. Oh yeah, of course, we also talked about the force law, which is very useful. The idea that there's this thing called a magnetic force that's placed on charged particles. They have to have a charge, they have to be moving, and they need to be in the presence of a magnetic field, and they have to be moving in such a way that they're not parallel to the field, because if they're moving in the same direction as the field, there's no force. They only feel a force when some component of their velocity is perpendicular to the force, and that's why you have a cross product here. We also talked about torque on current-carrying wires, which allowed us to then discuss how motors work and how generators work due to these type of forces. And then we talked about Ampere's law. Just making sure I'm not missing anything here. We talked about Ampere's law, which allows us to find the size of the magnetic fields in a more simple way than the Biot-Savart law, in a more theoretical way. Ampere's law we used this today. B dot dl is equal to mu naught times I. We talked about the force between two conducting wires. We looked at the magnetic field produced by different types of wires, all that kind of stuff. And then we get into what I find to be the most interesting part of this course, which is electromagnetism, the way in which electricity and magnetism relate to each other. When we talk about magnetism alone, we just say that currents produce magnetic fields because we observe that. We said that, you've got a current-carrying wire, you can put compass needles around it, and you can show that there's these circular magnetic field lines. And then you can use the Biot-Savart law to kind of describe how that works. With electromagnetism, we learn about Faraday's law, which is really, really powerful, and it's an idea that really it powers the world. Like this is where all the power, electrical power that is produced in the world is coming ultimately from how Faraday's law works. Faraday's law describes the idea that if you have a changing magnetic flux, you're going to produce an EMF, and that allows us to make it so that if we rotate a magnet near a coil, we can basically generate electrical current, AC current, and we can use that to do things for us, to power things for us. Faraday's law then leads into this concept of inductance itself, the idea that the property of a wire to produce a magnetic field can actually be used to store energy inside of something that's called an inductor, which is basically just, it's a bunch of coils of wire. We use that to describe how solenoids work, right? We could find the magnetic field of a solenoid. That really comes from Ampere's law, but solenoids end up being effectively what an inductor is. That's inductance. And then once we have this thing called the inductor, we can now kind of put everything from the previous chapters together in the form of the AC circuit stuff that we discussed with phasors and deriving things, and we learned about the idea of impedance and how you can say that V is equal to IZ becomes our new Ohm's law equation, basically, where Z is related to capacitors, inductors, and resistors. And you all should have that pretty fresh in your mind here because we did that last week. And then finally, the final topic of electromagnetism is the idea that when you combine together Ampere's law with an additional term, the additional term that Maxwell adds on here, which is that you also have to have the time derivative of the electric flux in here. Once you do that, then it turns out that when you eliminate the I term for free space with no currents, that you can prove that you get electromagnetic waves, which we've discussed obviously over the last 2 days, so I'm not going to go into a lot of detail about this. But that's it. That's the course. That's what we discussed this entire semester. And it feels like a lot of stuff. It is a lot of stuff. I mean, electricity and magnetism is... There's no doubt that it's harder than 1A. Definitely harder than 1B. I don't know about 1D, because like I said, I haven't taught it at the school. But it's definitely really challenging because there are so many different topics, and it's very difficult to see the big picture, right? It's really hard to see what the big picture of what we're doing here. And I really think that the big picture is that we're not doing anything that's that much different than Physics 1A. In Physics 1A, we basically discussed number 1 and number 2 here without electricity, right? Physics 1A talks about things that are sitting still, equilibrium, and things that are moving, which are things that are moving are governed by conservation of energy momentum and angular momentum and Newton's laws, right? So we talk about statics and dynamics. And in Physics 1C, we do the same thing, but we just apply it to charges. And when you apply statics to charges, you get all this junk, which is electric fields, right? Gauss's law to tell you how to find them. And then when you say, what happens when the charges move? Okay, we get this new idea, it's current, and we get Kirchhoff's rules and stuff like that, right? And then we say, oh, it turns out that when some currents move, that actually produces magnetism. So now we need to understand magnetism. How is this produced? And so we come up with some rules about that. And yeah, it's all complicated, and the details are challenging, the math is hard, and all that kind of stuff. But at the end of the day, all we're doing is saying, this is what happens when you have electrical charges moving down wires. They produce this effect called magnetism. And you already know what magnetism is. You knew what a magnet was probably when you were younger than 10 years old or so, right? When you play with magnets and toys, or when you see magnets on your refrigerator and kind of wonder what they are. So magnetism is not something that's new to you. All that happened in this course is you learned that magnetism comes from electric currents, which hopefully you understood from number 1 and number 2 here, right? And then the last section is definitely really challenging. Electromagnetism is definitely a new idea. There's really nothing in Physics 1A that corresponds to electromagnetism, because there's also nothing that corresponds to magnetism. But it ends up being this really fascinating idea that moving magnets produce electric fields, and moving electric fields produce magnets, basically. And we can use that to do all kinds of interesting things, including show that light is an electromagnetic wave. So that's what we discussed this semester. That pretty much covers everything. I'm looking back at the book to make sure that I didn't miss any major topics, and I don't think I did. There's other minor topics that show up in here, I mean, there's like transformers, which we really didn't talk about, but I'm sure you guys... We did talk about it a little bit, but not like in a lot of detail. But that is pretty much it. That is all of Physics 1C. So you're going to be tested over primarily number 3 and number 4 here, because the first exam covered number 1 and number 2, right? But that doesn't mean that you don't need to know all this stuff to do well on the final, because you're going to need to know what a capacitor is, right? You're going to need to know what an electric field is. You need to know what electrical current is, and you need to know Kirchhoff's rules to some extent. So you can't forget all this stuff, but if you want to study for the final exam, you're going to want to study number 3 and number 4 here, right? The things that come from chapters 27 through 32. So those are the primary chapters that the problems for the final are gonna be like. It doesn't mean that some of the problems you get might not come from these first 2. It's just primarily the problems from the final are going to come from chapters... Oh, no, I didn't want to do that. Definitely didn't want to do that. Oh, God. I can't wait till I don't have to use OneNote anymore. It'll be amazing. Maybe 2 more semesters. So chapters 27 through 32. That's not much, right? It's six chapters. It's really not much. And the first, exam will be next Tuesday. So, I know you've got other classes to study for and stuff like that, but you could at least skim through these chapters, in that time. I'm not saying you could read every chapter, but you could at least skim through them. If you've been studying well in this class, you've probably been reading some of these chapters anyway, so you probably don't need to cover everything. You just want to go back and review everything to make sure you remember all the topics. And remember, of course, that this exam is going to be just like the first exam in the sense that I'm going to give you your problem 3 hours in advance, so you're going to have plenty of time to work on your problem. And if you need to use your textbook, you'll be able to go back to the textbook, right, and and look at the way that they're talking about, or you can go back to your notes or whatever you want. So that's my review of what we've studied this semester. Did I miss anything? Is there any questions that anyone has?
Seems all good. Then you can like kind of give an advice for when we actually explain it. Like it did.
Sure.
Like, was there a pattern that was kind of something we shouldn't do?
Sure.
Some like a lot of students did.
We can talk to that. Yeah. So the biggest things you need to worry about on the final are clarity of work and clarity of thought. So you need to show all your steps. You need to show units on everything. If you draw a diagram, for God's sakes, draw it legibly. If you can, draw it in a way that uses straight lines, and if you're using a program like this, that'd be great. If you're going to be using like a camera and you're going to be like videotaping yourself while you're working on a piece of paper, just try to make the work neat. That's going to be part of what I'm grading you on, is like how clear what you're explaining is. And the way that I'm going to look at it is, if you were to explain what you're explaining to a student, would they understand it? That's the kind of perspective that I'm going to come from. Because all the problems that I'm going to give you, I'm obviously going to know the answer to. I'm going to know how you're supposed to solve it, right? But I'm not going to be judging you based on your ability to explain it to me. You should be explaining it in a way that you could explain it to someone that just started taking this class or something like that. Or to basically, you should be presenting the problem in a way that another student would understand it, basically, not in a way that I would understand it. That means you can't skip a bunch of steps that are important. That being said, the biggest problem that we're going to have is time. Time is our main constraint here. There are about 30 people in this class, and that means we have about 10 minutes per person for each problem. So when you're presenting your problem, you should practice in advance and get good at doing the problem. You have 3 hours, and you have one problem, so you should solve that problem multiple times, and then after you're confident that you believe in the way you solved it is correct, you should find somebody else to try to explain it to and time yourself. So explain it out loud to someone else with a timer and try to get it done in 10 minutes. And you should practice it once or twice before you come to class. And what you should be trying to do is to cut out anything that is unnecessary. For example, if you're doing a calculation, okay? Let's go back to one of these problems. Like right here. If you're doing a calculation, okay, and I see your question, Uzier, and I am going to answer it, but just getting there. If you write in your problem this piece of information, I guess you would also need to write down the radius, but it's given right here. And then you get to this line right here, okay? During our classes, I always put the numbers in here, right? During your presentation, you do not need to do that. As long as every variable that you have inside of here is defined, you can just tell me what the answer is, okay? That will save you an immense amount of time. It probably takes at least a minute every time I write out these things and then do the calculation, right? So have the calculation done beforehand and then just put the answer down. You don't need to plug all the numbers in, right? I can see that. Does that make sense to everyone?
Yeah. Yep.
Okay. That will save you a lot of time. In addition, you can skip steps, but if I ask you to explain a step you skipped, you need to make sure you can explain it. So I'm okay with skipping steps, but there are definitely going to be steps that I don't want you to skip. Now, you're not going to know what those are, like, a priori. You're not going to know them going in. You're not going to know what I want you to explain, maybe. You should know, honestly, but you're not necessarily going to know. So use the criterion of, if I was explaining this to another student, would I need to explain this step, okay? And if the answer is yes, you probably want to try to explain it. That being said, try to get the whole solution down to 10 minutes if you can. You can absolutely do it. Yeah, Uzair, exactly. It wastes a lot of your time, right? What do you say? You really messed up. You were screen sharing it. It was pretty slow drawing with your mouse. Okay, my recommendation is, probably not that you hold your phone, but maybe you get somebody else to hold it for you, or you find some setup where you can put your phone on top of some surface so that it's looking down at your device, or at your piece of paper, or, you know what I mean? Just practice it. You can get into Discord, and you can screen share, and you can just practice it until you can see like that your work is visible. You know what I mean? Like you can do that. I don't know if it was this class or my other class that, someone like just had their brother basically hold their phone above the thing. Or was it you, Jacqueline? Is that who it was? Yeah, that worked really well. Your presentation was really good. I think that's a great idea. I know someone from another class used their laptop camera, like their webcam on their laptop, and basically just like tilted their webcam down so that I could see their paper. It's not 100% perfect, but I mean, like, as long as I can see your work, as long as I can read it, as long as it's legible, it's fine. And you can test out all these things in... Yeah, that's a great question. Is it okay to set up a picture of your diagram before you start the screen like last time? Most likely, yes. Most likely it's okay if you put your diagram on there in advance. But be ready for me to ask you questions about why did you do such whatever, okay? So it definitely saves a lot of time. So, no problem. Most of these questions from this latter half of the semester, like look at what we're talking about. It's magnetism and electromagnetism. Just think back to what those homeworks were. Go back and look at those homeworks and try them again. And also, redo the lab manual problems. I'll try to grade the lab manual this weekend. I hopefully get it done before your guys' class. That should be fine. I should get that done. Look back over those problems, just look back at what types of problems you saw and go back and try some of them. I think you're going to find at this point that they're not that hard for you anymore. I don't know how hard they were for you the first time you did them. I don't know if you all were really struggling with these homework problems, but hopefully in retrospect, when you go back and now that you've seen kind of like the entirety of this course, like I hope that, you go back and you think it's easy. I mean, that'd be great. Maybe that's not the case. Maybe you're all still really struggling with these concepts. I don't really know where everybody's at because I'm not working off many facial reactions or anything here. The normal ways that I would know if people were doing well, but everyone seems to be turning in their homework, and you all did quite well in the first exam, so I think you all will do pretty well in this test too. Just remember, it's a big part of your grade. It's worth like 32% of your grade. So I know you've got other finals. I know you've got other projects. I know you've got a lot of other stuff going on, but you're going to want to put, like, during those 3 hours that I give you the problem, put some time in, Put some time in. The time you put in is going to be directly related to the grade that you get, Whatever you put in, you're going to get out. So if you get the problem and you solve it once and you show up and you do a really bad presentation, even if you understand it really well, that sucks. That's a bad way to lose a lot of points, So don't do that. You're all very smart. You're all very talented. You've gotten this far through the 1 series. I'm sure you'll do just fine. And you'll be done with 1C, which, even getting to this point in the course is it's a pretty big accomplishment. Because like I said earlier, most people are really afraid of this course. Hopefully, you can feel like when you're done that you're not so afraid of it, and maybe start teaching people that you shouldn't be afraid of this course. I left off a vector symbol. Yeah, I guess that's in general what I have to say. Your work needs to be neat, clear, and you need to be able to answer any question I ask. And prep in advance. Get in Discord and test your setup and make sure that it can be seen. You can get one of your friends to come and can watch it too, right? There we go. That's all I have. Seeing as I won't really see you all at all, hope you all have a great summer, and good luck with all your transfers, and good luck at your 4-year universities, and good luck with your careers and all that kind of stuff. I'm sure you all do really well. You're setting yourself up for success by coming to El Camino, I think, and I hope you all do really well. I'm sure you will. You're all doing a very good service to society by studying a STEM field, because we are in dire need of people like you that are interested in mathematics and computers and science and engineering. So, good luck to every one of your transfers. I hope you all get into the schools you want to go to, and remember that as long as you get into a school, it doesn't matter what school it is, you're going to have a great time. Hopefully by the time you're actually going to your 4 years, you can actually The world will be open again, as it should be, and you can really enjoy yourselves. So, yeah. Thanks, everyone. I'm going to stop the recording now.